Hello there everyone, thank you for joining me today as we discuss the fundamental theorem of algebra and how it relates to finding all roots of a polynomial. So a little warm-up exercise here. Here's something similar to what we've done in the past. Previously we have found the roots or the zeros of a polynomial by factoring. We're going to do that again here. We're going to solve this equation by factoring. So we have ourselves a quartic trinomial. Recall we can acquire a quadratic pattern, recognizing though that we need x squareds here, and factors of negative 15 that add up to 2 are 5 and negative 3. So we set these factors equal to 0 and solve, and we've done this before. The idea is to isolate the x squared and then solve using square roots, and anytime we have a negative inside a square root, we will need that imaginary number I to help us out. Well, to keep this video a little bit more brief, I won't go through all of those algebra steps here. So just kind of jumping ahead to what the answers would be. When you isolate x and solve using square roots, you will get these 4 solutions here. Emphasizing the word 4 because we have a 4th degree polynomial, and that actually leads us to the main idea behind this lesson today. Okay, that being the fundamental theorem of algebra. All right. The fundamental theorem of algebra gives us an idea of how many roots a polynomial should have. So if p of x is a polynomial of degree n greater than or equal to 1, then that polynomial set equal to 0 has exactly n roots. Now that includes multiple roots and complex roots, double roots, roots with the imaginary number I in them. Quick thought about irrational and complex roots. Those are roots that have the imaginary number I in them or some sort of square root in them, like we had in the warm-up today, actually. Well, if you've been thinking about it, when we've been solving for those type of roots, we've been using square roots. And anytime we solve using square roots, we use the plus or minus sign, which inherently gives us 2 solutions, right? There's actually a theorem about this called the conjugate root theorem that says if a plus the square root of b is a root, then its conjugate a minus the square root of b is also a root. And the same can be said for complex numbers. So we don't just get one irrational root or one complex root. They always come in pairs. Something to keep in mind. So, how are we going to go about finding all of those roots of a polynomial? Well, we're going to try factoring first. Usually the fastest, like we had in the warm-up today. But if factoring doesn't work, we have to have a plan B. So here's what we'll do in that case. We'll start by finding as many rational roots as we can graphically. Those are those roots that are not irrational decimals, they're terminating decimals or integers. We'll find those ones graphically. Then, once we have those, we'll divide them out to see what the other factors are that are left over. We'll use synthetic division to make it go faster. And once we know what those leftover factors are, we'll set those equal to 0 and solve to find the roots from those. We may be able to do that by factoring. We may have to use the quadratic formula. We'll see when we get there. Let's try an example. F of x equals x to the 4th minus 4x squared plus 9x minus 36. We're going to find all the roots, find all the zeros. This is a cubic polynomial, so we should have 3 total roots. That's what the fundamental theorem of algebra tells us. Well, remember, we're going to try factoring first, and here's a polynomial with 4 terms. We haven't factored many of these, from the start of a problem, but this is part of a technique that we have used previously. Previously, we have used the AC technique to factor quadratics. Well, part of that technique is something called factoring by grouping, where we have 4 terms, we look at the first group and the second group, and we factor out the common factor from each. That's what we're going to do here. We're going to factor this by grouping. So setting this equal to 0, from the first group we can factor out an x squared. We're left with x minus 4. From the second group, factor out a 9, we're left with x minus 4. We need to have the same factors here and here to proceed, because technically that factor x minus 4 gets factored out, leaving us with the leftovers x squared plus 9. Now that we have our factors, we can set them both equal to 0 and solve. I'm going to speed up the process here a little bit, keep this video as short as possible. When you set these factors equal to 0 and solve, you'll get 4 and then plus or minus 3i. We were supposed to get 3 total roots, and we did. 1 real root, which would show up as an x-intercept on the graph. 2 complex roots, which would not show up as x-intercepts on the graph. Here's another factoring by grouping example, since this is somewhat new technically. We'll set this equal to 0 here. From the first group, we can take out an x squared. We're left with x plus 2. From the second group, take out a minus 5 to be left with x plus 2. So we have x plus 2 that can be pulled out, and our leftovers are x squared minus 5. Setting those equal to 0 and solving results in roots of negative 2, and then what would be plus or minus the square root of 5. We have 3 total roots here. That agrees with the fundamental theorem of algebra and what it has to say about a cubic polynomial. Now here again is a cubic polynomial with 4 terms, but this time if we try to set this equal to 0 and factor by grouping, here we can take out an x squared and we're left with x minus 3, that's fine, but there's nothing we can take out here to be left with x minus 3. So factoring by grouping is not going to work here, and that means we now need to resort to our plan B. So remember, we start by finding as many rational roots as we can graphically, using graphing calculator or some other graphing technology, perhaps like Desmos, right? And to keep this video short, I'm not going to switch screens and show that. You can go to either of those resources, graph this polynomial, find any x-intercepts, and we'll take the rational ones, the ones that are integers or the ones that are nice terminating decimals like fractions. And if you do that, you will see on this example that x equals -1 is a root. That's one of our final answers here, and there's a total of 3, so we're going to get 2 more. Now, if x minus 1 is a root, that means that x plus 1 is a factor of this polynomial, but we don't know what's left after that. We're going to figure that out using synthetic division. So switching colors, because this is kind of a new step, -1 we know it to be one of the roots, so we'll set up our division now. And you could do long division if you wanted, but synthetic division is just so much faster. By the way, we know our remainder should be 0 because we're dividing by something that is a root. So here goes our synthetic division now. Series of multiplication and addition, right? And we do get a remainder of 0, which is comforting. We're left with x squared minus 4x plus 5. That would go in this question mark up here. That's the leftover factor. Well, if this itself were factorable, I would find its roots that way, but I can't think of factors of +5 that add up to -4, so here I will have to resort to the quadratic formula. Switching colors one more time. Here's A, B, and C. Quadratic formula would say that x equals opposite of b, 4, plus or minus the square root of b squared, -4 squared, minus 4ac, 4 times 1 times 5, all of that divided by 2 times a, 2 times 1. So here we have x equaling 4 plus or minus the square root of -4 over 2. And the square root of -4 reduces down to be 2i. Now all of that stuff is divisible by 2. 4 divided by 2 is 2. 2i divided by 2 is I. So here are our other 2 roots. Remember, we were supposed to have a total of 3. We got x equals -1 from the graph. We got x equals 2 plus or minus I by using the quadratic formula applied to that mysterious factor that we found using synthetic division. Let's try one more example of that here. It's kind of a new process. Here's a 4th degree polynomial with 5 terms, and we have not discussed how to factor that at all, and that's not going to be factorable for us here in this class. So right away we're going to resort to our plan B. We're going to find as many rational roots as we can graphically. Again, going to save time by not switching screens and showing you that. We have done that enough times already. This time we get 2 rational roots from the graph, -2 and +3. That means that x plus 2 must be a factor of this polynomial, x minus 3 must be a factor, but we don't know what's left. We're going to find what's left using synthetic division to divide out those factors. So switching colors, I'll divide out -2 first. 1x to the 4th, -1x cubed, -5x squared, -1x, -6. Our remainder should be 0 because we're dividing by what we know to be a factor. And here goes our synthetic division. Let's see, multiply and add, multiply and add. That's a +1 there, my mistake. Multiply and add, and we do get our remainder of 0, which we knew was supposed to happen. Now, we just divided out this factor here, this root, but we can do it one more time because we've got one more to work with. So, maybe I'll switch colors now. Now let's divide out 3. And again, we should get a remainder of 0. Multiply and add, multiply and add. Okay, we're left with x squared plus 1 as that mysterious leftover factor over here. Well, let's set that equals 0 and solve to find those roots. x squared equals -1. Solve using square roots here. We get x equals plus or minus I. So we were supposed to find a total of 4 roots. We found 2 from the graph right away. Those are rational real roots we could get right from the graph. The other 2 remaining roots were complex roots. We found those using our 3-step process. That's the process we will use to find all the roots of a polynomial when we cannot find them by straight up factoring. So that's enough about the fundamental theorem of algebra today and how it relates to finding all the roots of a polynomial. Thank you for watching.